How's the track treating you? Adil is at 9. Yo, this I don't want to butcher your name. And you and your surname is just as hard. Musarura. I hope I got that right. Musarura is at 8. Nozi is at 10. We have some high values here. Juliet is at 5. Juliet, I think you went down from 6. What happened? Was it the previous assignment? I wonder what dropped that scale. But happy to see that some of you are at like a good space. Hopefully that means you're enjoying it. I was having a conversation with a friend and I stated that some things are enjoyable when they challenge you, because once you finally get it, that satisfaction is a lot higher than something that you actually know and are good at. So don't take the obstacles as obstacles, right? Take them as an opportunity to get that high dopamine rush when you finally get something that you've been struggling with, right? It's like when you're running your code and you keep getting an error and you don't see it and you don't see it and you keep running. And at the end, you finally get it and your code is running well. It's like the best feeling ever. The dopamine rush is at 150% at that point. So never see or find any of challenges, never, not just in this program, but just throughout life. Never see the challenges as obstacles or something that would hinder your success, but more of an opportunity, because the feeling is going to be much greater than if it was something that you expect. So a huge surprise. Okay, guess that's my advice for almost closing to graduation of this track. Right, let's get started. So we are going to go through some coding, that is with k-means clustering. What is k-means clustering? It is a clustering or unsupervised algorithm, unsupervised machine learning algorithm, right? Now, I think last week we had spoken about dimensionality reduction, right? Yes, and we spoke of principal component variables, and I stated to you that one of those methods are clustering. Remember, when we're working with unsupervised learning, we don't know what's happening. We don't have a target variable. We're not sure exactly what we are trying to predict, what we're going to get as the expected output of given features. We want a model that's going to help us identify these patterns, these characters. And from there, we then draw up insights. So clustering or k-means clustering is one of those methods. And the learning objectives today is that we implement k-means clustering algorithm. We implement the k-means clustering model in sklearn, and we choose the optimal number of clusters. So in this case, you have to input these parameters or hyperparameters, where you state how many clusters you want. Okay, not sure. We have gone through hyperparameter tuning, correct, in the chat. There's so many cohorts running, I'm not even sure what's happening now. But you can apply hyperparameter tuning to make sure that your k-means clustering method is working at optimal as well. So clustering is the process of grouping similar data points. Last week, we had seen the circles, the square, and the triangle, right? Those were similar, 3 sides, 4 sides, and a circumference. So such that the data points in the same groups are more similar to other data points in that group than those in other groups. So as I stated, if we're choosing sides as a feature, or the pattern that we notice, or the color as well as one of the feature, we could see that no, these ones are or have the color red, these ones have the color mustard or yellow, and these ones have the color orange, right? So we don't, for example, we are just given that data. We don't know exactly, or the model doesn't know exactly what it is supposed to predict, but it can show you similarities of different data points. And from there, you will then draw insight from them. So in the example of the circle, the square, the triangle, we would then draw insight that, okay, in this data point, we have triangles, red triangles, we have mustard circles, and we have orange squares. Example of that can be we have middle income, so it can be categorized. We can have low income, middle income, and high income. All right, judging from how the model has clustered those observations and from the features, we then see that, okay, no, in this cluster, the average, let's say, income is 50,000. In this one, the average income is 120,000. And in this one, the average income is 200,000. Then we can then draw insight that, okay, we're going to have three categories of lower, middle, and higher. So the aim is to divide groups with similar characteristics and assign them to clusters. This will give us insights into the underlying patterns of the different groups or clusters. And in this course, we will explore three types of clustering, that is hard clustering, hierarchical clustering, and soft or fuzzy clustering. So in hard clustering is when observations belong to a cluster or it doesn't, right? What does this mean? For example, if we're going to do hard clustering for learners in a class, and we decide we're going to have male and female, and from there we'll see, let's say, top male student and top female student. That is hard clustering. You can never be in or be confused to be in either of those clusters. You're either male or female in that case, or you are a learner or not a learner, whether you are registered or not registered, whether you had passed or failed. If it is clustered and you have this data and we see that those with less than 50% are clustered and put into that group, and those who are higher than 50% are put into the other group. You cannot pass and fail at the same time. You either pass or fail. That is a pattern that we see. We see that the pass, or the model will see that those who have been categorized as pass have, let's say, exam score greater than 50%. And those who have been categorized as failed have an exam score of less than 50%. Then it would cluster them into those two clusters, and that would be hard clustering. Then we have hierarchical clustering. So observations belonging to child clusters also belong to parent clusters. Now, hierarchical clustering can come in different ways. One is agglomerative clustering. And I'll show you a video as we go down of how this is what we call a denogram. So you can decide, right? Let's say for distance, or it starts with each observation starts as a cluster, right? So let's say we have 150 data points or 150 observations. Then we have 150 clusters. Then we decide that, okay, if we want to join by distance, that is maybe 2 centimeters, or points that are 2 centimeters apart from each other. Then we form that cluster. Let's say A and B, they form a cluster, but B is also close to C. Now that also forms a cluster. And it continuously forms a cluster until you have reached the optimal number of clusters that are optimal for your context. Then we have soft or fuzzy. So an observation can belong to each cluster to varying degrees, correct? So it will depend how you are clustering. Or if you decide you want, in this case, 3 clusters, you would have observations on this side belonging to this cluster, that cluster. If you have 2 clusters, now you see that some of these clusters are now within this cluster here that we had in this context, as well as if you now go back to 3 clusters, depending on what context you're looking at, it would vary where your observation would lie. All right, for example, you can state, I want to cluster by distance, or I want to cluster by average or by variance, depending on how you want to cluster your observations. All right, so those are the three types of clustering. Mostly we're going to be working with your hard, in this case, your hard clustering, where we'll be using k-means algorithm, right? So how does k-means work? So this is an example of unlabeled data, right? In this case here, we don't know what's happening. We don't know what's going on, but we're seeing that there's some data points here, some data points are clustered there, and some data points are clustered here. This is not the most ideal situation, okay? You won't have data where it's very clear of the clusters that you have. But drawing up a visual will obviously guide you and see that, okay, I have data points acting some sort of way amongst these regions, and then decide how many clusters you want to create. And if that is at optimal, then you work with that. But there are ways to decide how many clusters you want. Okay. So k-means help us clarify what's happening here and identify that, okay, clearly there are three groups and they create their clusters. But how does this work? How does k-means clustering work? So what happens is that in your data, right, there are things, or with this unlabeled data, k-means will assign centroids, all right? So these are what we call centroids, but it doesn't start here. Hopefully I created a visual here. Yes, it doesn't start here, right? I mean, like the model just started learning what's happening. It cannot specifically identify that. Nope. In the first iteration, I will have a center here, center there, center there. And this centroid is the center of each cluster. Okay. So how it works is that in the first iteration, it will randomly assign centroids. So hopefully I can show you here. So we have data, all right? Then we state we want the number, how many number of clusters that we want. In this case, we have 1, 2, 3 clusters, right? We have the green, the pink, and I don't know, the mustard, right? So what happens now? The model now throws random centroids, just random. As you can see here, we have random centroids. And then after, it starts calculating average based on the points that are assigned to this centroid. Okay? And it then becomes sort of like the average of the clusters of points that are similar to this centroid and points that are similar within that cluster that is now have been created. So these are the steps basically. Pick the number of clusters, so that's step 1, and randomly assign each observation a cluster from 1 to k. You repeat the following until cluster assignments stop changing. So for each of the clusters, compute the cluster centroid. The kth cluster centroid is the mean of the observation in the kth cluster. So remember, k is the number of clusters that you want. Assign each observation to whose centroid it is closest, where closest is defined using a chosen distant matrix such as Euclidean distance. So as I stated in the first iteration, the centroid is random. If we state it as it is, it's random. Thereafter, it keeps calculating the average and centers that centroid into the average of those observation that form or are assigned to that specific centroid. Right? So if you see, these centroids are random, but it states that this is the centroid for these yellow observations, this is the centroid for these pink observations, and this is the centroid for the green observations. But as we keep iterating, as the model is training, the centroids start moving amongst or towards their points. The points that are similar together also move within or towards the centroid, and it forms a clear cluster by the end. Right, so that's how the model is working. It creates a centroid, creates the clusters that you specifically want. Each of those clusters have a centroid. Then what do? I understand the data points that are around me, and it puts itself into the center of those data points, and that is the centroid. All right. Hence the term centroid gets derived from center. It is that now at the center of this data point. Okay. So let's code up this k-means clustering algorithm. We're going to set up synthetic data. Why do I want to do this? So that you can see how it works with clear evidence, right? So we're going to have synthetic data of which it will have already on its own sort of clusters. But we're now going to work backwards, right? We're going to say, oh no, I just have the data without the centroids. And now I want to see how k-means clustering works. And the evaluation matrix and the assumptions do help me into going back to those clusters that I know I had in the beginning. So I think some of the new libraries that you'll see are the make blobs, your standard scalar, your matplotlib, and your seaborn, as well as your pandas. So we're going to run that. What's going on? Okay, going to run those libraries. Just give it a moment. Great. Then we're going to make blobs, and we're going to have 2 features just to have it simpler to visualize, and 8 centers. You can change this, right? For, I guess, practice purposes, you can change the centers to say 5. And we're going to make blobs, and we're going to have 1,000 observation centers tell us how many basic clusters we're actually going to have. The number of features we stated is 2, and random state is equal to 68 for reproducibility. So we create this data. This part is us creating this data, and once we run that, you'll see that we have now specified or created data that have specific clusters. And if you see, we have 8 clusters, right? We have 1, 2, 3, 4, 5, 6, 7, 8 clusters. This is synthetic data that we have created so that we can test the methods and see if we can come back to this without knowing that there are 8 clusters, right? Great. So this is the data that we have, right? And each one, that Y is the cluster it sort of belongs to. We have feature 1 and feature 0. So, however, as stated, we are working backwards, right? In unsupervised learning, we do not have access to these labels here. As such, let's pretend we don't know the number of clusters and pretend that we just came across the following data set. What do I mean by the following data set? We remove the Y. We don't know which one belongs to which cluster. And now we're just back to point 1. You've drawn up your data. If you have more than one feature, you can use principal component or dimensionality reduction to help you see how your data is distributed amongst the 2 features or the 2 principal component that you have. Right, given that that principal component explains enough variance. So this leaves us with 2 problems to solve. We don't know which pair of features belong to which cluster. We don't even know how many clusters that we have in the data set. So we usually address the first problem by building a clustering machine learning model, and we address the second problem by making an educated guess of how many clusters there are. So as you will notice with the k-means algorithm, many clustering algorithm requires that we first select the number of clusters before training the machine learning model. So as stated, you can use hyperparameter tuning as well to see which cluster works well. But in this case, there are methods to see which cluster helps the model perform well or optimize the model performance. So as usual, we're going to pre-process the data. All right, so it is good practice also always scale our data, and we're going to use our standard scalar. We're going to run that. But as stated, before even training the model, we need to tell it how many clusters it should identify, right? And let's say we just looked at our data, and we're like, okay, this looks like a cluster, that looks like a cluster, that looks like a cluster, say 1, 2, 3, 4, right? So we're saying 1 cluster, 2 cluster, 3 cluster, 4 clusters, right? You can go ahead and guess, or you can have 3 just to see how wrong your assumption is. I mean, like in the beginning, we know that we have 8. So even my 4 is incorrect. So as stated, we decide on the number of clusters that we want to select, and we state that k is equal to 4. We then call the k-means clustering. We're just going to import that cluster library. I haven't run this guy. And we can import the date and time just to see the runtime of the training model, or once we run the code. Not necessarily important in this case. Maybe if you are comparing how each model performs, you can share the runtime for that as well. So we call the k-means function, or the algorithm, and as stated, we are asking it to give us 4 clusters and a random state of 42, and we fit our X scale data. What is our X scale data? That is our feature 1 by feature 2 data, right? DF with no labels, that is our X scaled. So we run it, and it's going to do what we had stated in the beginning. What does it do? It's going to assign and be like, okay, no, I'm going to assign you to this cluster. I'm going to create centroids. I'm going to keep running my centroids and trying to center within the points that have been assigned to me. And hopefully that will help me create clear clusters. So we run that, and we want to now evaluate our k-means clustering and see how well is it performing. Did it identify the clusters that we have? We know that it's not 4, but as stated, we are going to assume that we don't know that it's 8. So we predict, we state that now, remember we removed the labels. So now with those predictions, we're going to create a new column called cluster label. And the predictions that the k-means, if either from 0, 1, 2, 3, will give us the data. So for example, if we run that and add another cell and call EF no labels, we now have cluster label. These cluster labels are the label that we are predicting a specific observation belongs to a specific cluster, right? So in this case, cluster 3, observation 1 is in cluster 3, observation 2 is in cluster 1, and so forth. You can see how many clusters by saying dot unique, or you can say cluster label, right? And then unique. What did I do? Did I not spell it? I don't think unique. My unique spelling. Wow. Right, and you'll see we have 3, 1, 2, 0, right? Those are the unique values within the column of label, cluster label. Cool. So then we say centers, and that gives us the specific location in our 2D or plane, 2D plane, that we have drawn up our observations towards. So it will give us, so for example, center 1 could be here, center 2 could be there, center 3 could be here, and maybe center 4 could be there, right? Those are the coordinates that we have right there. Right, so these centers are giving us the coordinate x, y, x, and y. So let's plot this and see how all these clustering methods work, and show the centroid locations and see if, okay, I selected 4 clusters. Let's see how well my centroids are placed and how well my clustering has gone, I guess. Right, so this centroid seems pretty well centered Here, I wouldn't necessarily say it's well centered. It seems like it's just divided the two, just cut the data in half, as well as this guy and that guy here. So it seems what you want to have your centroid with your centroid is that you want your observation sort of compacted within the centroid. You want minimal variance amongst the values surrounding your centroid. And if you see here, there's a point that is that far, and there's a point that is that far. This gives high variance within the cluster, and that's not what we want. We want small variance within the cluster. We want to make sure that the values within that cluster are similar. Remember, clustering is grouping. If we look at that definition, where is it? Clustering is the process of grouping similar data points together. Now, if you look at this, does it look, where are we? Here. This point is definitely not similar to that guy. They are far apart. How can we say that these two are similar? The variance between them is quite high. So we can't necessarily say these values are similar. But we don't want to play mind games and testing the human eye. We have ways to find and decide the number of clusters that will give or optimize model performance. One is a term we call within cluster variation. So we'll make use of a technique called the elbow method to determine how many clusters to choose. So for each cluster, we will measure the total within cluster sum of squares. So what does it mean for each cluster? It's going to keep testing. If we have one cluster, how is the within cluster sum of squares? When we have two clusters, how is the within cluster sum of squares? Who can tell me whether we want, so in the chats, right? So I've been talking for long now. Let's hear what you guys have to say. Who can tell me whether we want this value to be high or low? So if you look at the definition of within cluster sum of squares, it is computed by calculating the sum of squared distances between cluster centroids and the data points that belong to them. Adil says low. Yes, that is correct. Within cluster, sum of squares is the variation. Within cluster, variation. How different are the points within these clusters from each other? Yes, Musarura. That is correct. We want that value to be low. We don't want those values to be high, because then we know that no, man, these values are not similar. So within cluster sum of square is a measure of similarity of the observations within our cluster. Lower WCSS means that a cluster is more tightly grouped. So naturally, as we increase K, within cluster sum of squares will decrease until K is equal to the number of data points in our data set. But we don't want to do that. We don't want to have, if we have 150 observations, we want to have 150 clusters. No, like we might as well have done nothing at this point. But we want to have a or number of clusters such that your within cluster sum of squares is at its minimal. Not zero, but at its minimal and sort of like reasonable. How do we do this, right? We first test cluster 1 and check the within cluster sum of squares, cluster 2 within cluster sum of squares, cluster of 3, and we have within cluster sum of squares. What we want to see is at the point where the change in within cluster sum of squares, as we increase the number of clusters, sort of starts decreasing at, I would say, a constant rate. Why? Because that means now at this point, we are separating points that are the same. if the within cluster sum of squares is not changing that much anymore, that means as we keep on creating clusters, nothing new is changing. Nothing new is changing. Now we are within the clusters. And obviously, what will be different from this point and the next if we add another cluster? Not that much. All right. So within cluster sum of squares, it's very important to identify how many clusters you want. And a method that will be used within cluster sum of squares is your elbow method, right? So we have chosen a range of values for k between 1 and 20. And for each value of k, we will run the k-means clustering algorithm and record the within cluster sum of squared, referred to also as inertia in sklearn. However, for reasons that will become obvious later, we will implement our own WCSS here. Okay. So first things first is we define that within cluster variation. So what am I doing here? I'm writing off this calculation there, right? We're summing that up. So let's try between, so we've now created that function of within sum of squares. And now let's try to test this within cluster sum of squares. Cluster, we're going to run it, and we're going to append the within cluster variation as we move. Okay, so now that we've performed the clustering for each between, let's see how we can plot this guy here. So these are as our within cluster sum of squares values for I told you that by the time your within cluster sum of squares sort of move or decrease at a constant rate, that's when you know you have your optimal number of clusters. So as we scroll down, we see that's a huge decrease. That's what's happening. Why did the recording stop? Okay, great. So as we move from each cluster, right, from cluster 5 to 6, okay? It's decreasing from cluster 6 to 7. Then you start seeing that, okay, from 7 to 8, it kind of looks the same as from 6 to 10, 10 to 12, and 10 to 11, and 11 to 12. The within cluster sum of squares isn't changing that much. So have we reached optimal? Where? Who can tell me where we've reached optimal in the chat? Who can tell me whether or not we have reached optimal? Where we have reached optimal? Which number, how many number of clusters have we reached optimal? You guys all there? 4 to 8. Ideal if you say 4 to 8. So which one are we going? You're looking at 4 to 8. Okay, but remember your model, I guess then you can use hyperparameter tuning, where they use grid search or random search, and you select those, or test with your 4, let's say 4, 6, 8, and see how well or which one gives the best, or which parameter optimizes the model, right? You can try that if you're not sure, if you feel like you're looking at it and it's like, well, 6 then. You're saying 6. Okay. Why 6? Yes, I mean, like in the human eye, it looks like at the elbow, but we also have another elbow here. Why not 4? We tried 4, okay, but it didn't work, so we can state that. So when you want to read the elbow method, you want to look at the elbow, right? We've already tried 4, and let's say that's an elbow point. That's also sort of an elbow point. So we're saying maybe 6. So let's try 6. All right, let's see what happens when we have 6 clusters. So using the elbow method is as simple as observing the plot of within clusters for each number of clusters and deciding whether the elbow, as stated, so you can have an elbow there, or an elbow there, or an elbow there. The elbow is closely defined as the point at which the WCSS curve has its greatest decrease in slope. In other words, it is the point after which adding another cluster does not meaningfully decrease your within cluster sum of squares. So below we've used a code to generate the elbow method plot from above. So once we run that, it's just basically adding a line of seeing the elbow. Like, okay, cool, I'll take, as stated, I think Adil said 6, right? Abdul says 10. Whoa, Abdul, you're like here. Well, you can try that as well. As stated, you can use hyperparameter tuning and see. Adil said 6, so you can cut that at 6. If you wanted to cut it at 10, you'll just go here and say 10. We run that and you see that now our line is at 10. Right, so it's just showing explicitly that, okay, maybe someone is reading, you then identify that where your WCSS didn't show that much change was at k is equal to 10. And you can use that method, right? So let's just keep it back at 6. Run that, right? So we then decide that, okay, my elbow would be at 6, and I'm going to now try and train my model at k is equal to 6 and fit my X scale data. As I stated, that runtime was 0. So that was less than a second. That model trained within less than 1 second. So we run that again and we create a visual to see our centroids, right? So, okay, that's not bad. I mean, like, if you look at it, we have k is equal to 6, has a center for here. We have a well-centered there. We have a well-centered here. We have a well-centered. Our centers are pretty good, right? But we know that we have 8, all right? We have 8 clusters. So just to show you that, do not just end at elbow method, right? Make sure that you are not just looking, for example, at points. Oh, what am I doing? At points that you see there and you're like, okay, no, that looks good. Or points within a cluster. Remember, within cluster sum of squares is looking at points within a cluster. You also want to look at how different are these clusters, right? How different are these clusters that I am now creating or the model has identified? So who can tell me whether between cluster variation should be high or low? High, exactly. It should be high. We want our clusters to be different. We want to make sure there is clear difference between our clusters, just as much as there's a clear difference between someone who passed and failed. Yes, there may be 49 and 51, and those values only differ by 3%. Is it 3? No, 2%. My math's my word. 2%, but they're not the same. Okay, they're from different clusters at the end. So what we have now is the between cluster variation. This is where we check how different, what is the variance between or across these clusters. We also have, what do we call we also call it intra-cluster variation, but in this case, between cluster variation. Same formula here, where N of K is the number of data points in the cluster. C of K is the centroid of the cluster, and X is the mean of all the data points. All right, not in the cluster. No, that is the mean of all the data points, not just the data points in the cluster. That is the whole observations of values. So we're going to implement this method just to show it as, so we have the global mean as stated, that is the mean of all values. We have our centroids. Remember, the centroid is, you see how it groups by column, label. We have mean for each centroid count and centroid mean distance. Okay, so that is now centroid minus the global mean to the power of 2, and we basically sum all of that and return. Run that to get our BCSS, so our between cluster sum of squares, which is also between cluster variation. When you see sum of squares, that's usually variation. If you look at your variance formula, you'll see something similar to that. I think xi minus x bar to the power of 2 divided by n minus 1, something like that. I stand to be corrected. We run that and we look at what this looks like. So because BCSS is sort of the inverse of WCSS, you're going to get the same visual, just reflected now on the x-axis. So if you look at that, you have different elbows. You have an elbow there, you have an elbow at 8, and I guess I think who had where you have 10, Abdul said 10, right? If you were to reflect this on the x-axis, you would get the same graph or curve as your WCSS. Right, but is that enough? No, that's not enough. So just as much as when we have precision and recall, there's always that one matrix or value that balances the both. And in this case, we have what we call the CH index, right? So this gets the ideal scenario where our clustering assignment have a small WCSS and a large BCSS. So the CH index basically combines these two so that we can optimize on both of them, and that will basically help us optimize on the number of clusters that will help our model perform well. So there's a lot of optimization. You want to make sure you optimize the between cluster variation, the within cluster variation, and basically the model in itself. So we calculate that CH index, we run that as well, and we look at what that looks like. And what you want to look like at in this case are your peaks when reading the graph. At peak is where you will find where WCSS and BCSS have been optimized. And if you look, the peak in which we have optimized is at, oh my word, where's that line? Let's draw that line. Where did we draw that line? Just want to copy that line of code. Way here. Let's draw a V line. We'll copy that. And where's that peak? Just to show you how that's exactly. Oh man. Where did I say? That's 6. Oh, we want 8. right? That peak is exactly at K is equal to 8 clusters. And we know that we should have 8 clusters. So this is the power of the CH index. Like, okay, you have made sure that there is low within cluster variation or low within cluster sum of squares and high between cluster variation or between cluster sum of squares. And you found the point or the point at which these two are at optimal in a manner that we will get the optimal number of clusters. Remember I stated you want to optimize BCSS, you want to optimize WCSS to optimize the number of clustering and therefore optimize the performance of my model. So as much as, yes, these methods are good, you always want to go a step further to make sure that I'm not just optimizing BCSS or WCSS. I have made sure I optimize each or every single important metric to help me get the correct number of clusters. So here we see a very obvious peak at 8 as stated. You guys can read the rule of thumb here to investigate each peak. This include K equals 4, 8, 13, 16, 19 in case where things aren't clear. In this case, however, it is super clear that the obvious number of clusters is 8. So if you have an obvious peak, you know that, okay, that's like my highest peak, correct? So I'll select that guy. But if you had multiple peaks and you're not sure which one is, I guess, the highest peak or the peakest peak, and then you'd have to analyze each one. All right. So let's look at what we have now. We're going to fit our model with 8 clusters and see how we are performing. We're going to run that and plot. And there we have it. We have 1, 2, 3, 4, 5, 6, 7, 8 clusters, which is exactly the same as what we had created in the beginning. Wait, there. 1, 2, 3, 4, 5, 6, 7, 8 clusters. And if we look at our clusters, now using our human eye, we see that, okay, this point, remember, I think, if we look at this guy, not this guy, I think I was at 4. 6 isn't that bad, but 4 was horrible. Look at this point to that point, right? And I stated that the variation between this point is definitely high. That point can definitely not be similar to that point there. If we look here now, our points are similar. The variation isn't too bad. They are closely stacked within the centroids for each cluster. We're not thinking, oh no, the cluster just halved these data points and decided, yeah, no, we're going to have centroids there because it's at the middle of the data. The points should be close to the centroid. They should be hugging the centroid. Not that the centroid is separating the cluster into half and half. No, that means there's something that we're not getting right. We don't want this. We don't want this one. Looks like it's separating the cluster, or in the worst case, what was it? Is this the 4? No, this is K is equal to 6. I'm looking for K is equal to 4. Yeah, right? We don't want this. We want our observations or our data points to be hugging our centroid. They are the center of their lives, I guess, right? So in this case, it is separating the data. It is not centralizing the data. It needs to centralize the data to be a good centroid. And all these steps help us get to that point. It helps the model understand the data points and perform and create these clusters. Right, this looks great, but for good measure, let's compare with the original data set we created, which is exactly that. And we see we have those 8 clusters there. Just like every single model, we have evaluation matrix. One being the silhouette score, and the other being the Davis Bolden index. So the silhouette score is a measure of how similar an object is to its own cluster or cohesion compared to other clusters. So now what it's doing is that it's looking, it's like, why is this not in this cluster? Right? What are we sure? Like it checks, are we sure? Now that we have clear, defined clusters and we're happy with them, let's say, or assume that we have not evaluated, guess the matrix. We have used all matrix and optimized all matrix to select the optimal clusters. Now we need to see, okay, we found the clusters, but with the points within the clusters, why is this point in this clusters compared to the other cluster? Is it truly closer to these clusters than points in the other cluster? Right. You can read it ranges from -0 to 1, and we know that from 0.71 to 1, that is a strong structure. That means your clusters are clustered well. You have a low WCSS and a high BSCSS. 0.51 to 70, you have a reasonable, and 0.6 to 0.5, you have a weak structure, and basically 0.25, you have a non-substantial structure. So we know that we want to see now please note that with your evaluation matrix, right, you may see that it's good, but most companies will have a limit. Let's say, how does it work? If you are a data scientist or a machine learning engineer and you test all these models, different companies have different accuracy scores. You can work in a company and they will require that when you are working with a model, you need to make sure that your accuracy score is at 95% or higher. So you need to gauge as to how accurate is my model, how well is my model. You need to be looking as to, do I need to have my silhouette score here or there? Obviously, if they want an accuracy score of 95%, then it's probably with a strong structure. So let's run our silhouette score and see what we have. We have 0.57. This indicates a reasonable structuring algorithm or cluster, right? So the silhouette score of 0.56 indicates a reasonable good clustering result, shows that they are fairly distinct and well-defined with minimal overlap between them overall. Overall, it indicates a relatively successful portioning of the data into meaningful clusters, right? So not performing too bad. Again, it is synthetic data. I was hoping it would be obviously around 0.71, but as stated, it is a reasonable structure. So remember, when we say you're drawing insight, you need to gauge if this was age and income of what insights you're going to have. This can be young, low spending. This can be middle or the older youth, middle spending, and this can be elder, high spending. You draw up your insights of what the clusters are going to give. With 8 clusters, I'm not sure what you would say. What would be the scenario? I guess it depends on the context, but from the clusters is what you then read, and from the centroids as well. For example, those centroids, these centroid values, where is it? Where were the centroids? Where were the centroids? Where are my centroids now? Let's run back from the beginning so I can find them properly. We ran the feature, we're creating the data. We ran k is equal to, there we are, right? So this would be, let's say, with the, let's take the first 3. Lower or higher, middle, lower income. These are the centers. So you can say this has an average 8 of 8, an average age of 8 and an average income of 3.38 million, let's say, right? So those centers help you classify that, okay, anyone who's within this average or the young, lower, lower, middle, or high income, those values and the insight can be drawn from your centroids, right? So the model just helps you identify patterns and what it sees amongst the data. You now have to draw up the insight. You cannot go to a stakeholder and say, yes, I have 8 clusters. You have to tell him what are these clusters? What are they telling me? What are you working with? What is the state? I don't understand. What groups are these? Okay, so you need to now clarify what is happening there. Then we have the Davis-Bouldin index. Now, the Davis-Bouldin index is another measure of cluster validity that evaluates the average similarity between each cluster and its most similar cluster. So now it's just the same. We're working with observations in the beginning. Why is this observation different from the other? And how similar are these clusters? We want these to be low. Do we want them to be low? Wait, let me think. The Davis-Bouldin index calculates the average similarity between each cluster and its most similar cluster. It is defined as the ratio of average intra-cluster distance. So we want this to be high, all right, as well, because it tells us, as stated, the intra-cluster distance between cluster centroids. So now it's looking at or measuring how different your clusters are. Did you separate, or as with your silhouette score, does your observation belong to this cluster as to against the other cluster? And with your Davis-Bouldin are these centroid, how is the distance amongst these centroids? And that then also can help us state whether this K-means algorithm worked well or didn't perform well. And if we run that, we see that we have a Davis-Bouldin index of 0.598. So this is a relatively good clustering result. It suggests that the clusters are reasonably well separated. So if you want to see how your individual clusters are working, you look at your silhouette score. If you want to compare amongst clusters, you look at your Davis-Bouldin score. Alrighty. Then there are some advantages and disadvantages of clustering, just like using any other machine learning model. Right now, I was having a conversation with my friends as well, that most people in corporate avoid K-means clustering, mostly because you can be in a situation where you have multiple features. You can have a row of 51 features and you want to use K-means clustering. That's a lot. It's suitable for large data sets. Sorry about that. Easy to implement and interpret, easily adaptable to new data sets. Disadvantages is lacks consistency, sensitive to scaling, and dependent on initial values. So I wanted to show you a video before we close off with the hierarchical clustering. Also note that there are extra resources on how to choose the number of clustering, how many clusters, this is a hard problem, and so forth. So extra resources have been shared with you for you to read through that. But there is what we call, in this case, the hierarchical clustering. So remember, we had just gone through the hard clustering. But I want to show you a video of how hierarchical clustering works. And I've just attached that video here. I'll give you a moment to read that.
So let's look at the simplest And then the next
All right, so that's with your hierarchical clustering, and the method they use is agglomerative clustering in just as much as what did we have? Hard clustering, hierarchical clustering, and soft fuzzy clustering. So hard clustering is k-means clustering. Hierarchical clustering is agglomerative, or a method uses agglomerative clustering. Now, I noticed that when he was speaking, you couldn't necessarily see because of the, what do you call, the subtitles. So where he was selecting was that where you cut that line of number of clusters, or gain the number of or distance threshold to get the number of clusters, is that you look at the root of which you have cut, or your line cuts, right? So that line, so this one line gives us all this cluster. So we have A, B, C, D, E, F. I mean, A, B, C, D, E. This line gives us F. This line gives us G. We look for another line that this distance threshold cuts, and it's that line here, and this will give us H, I, J, K, M. Whoa, what's with the alphabets here? H, I, J, K, I would have assumed L, M, N, but M, N, L, I guess. And therefore we have these cluster, oh, I's on its own. Is that I or L? Anyway, so we look at this line, we look at that line, we look at this line, we look at this line, we look at that line. So everywhere the distance threshold cuts, you want to look at the root to get your clusters. All right, and that's how a dendrogram then works with hierarchical clustering. Okay, I'm going to exit that. Right, so I'm just going to close I hope you guys could hear me. Okay, great. I thought I was muted. I can hop on to the Q&A session. While we do that, I'm going to launch a poll and hopefully you guys can complete that poll for us. Are there any questions that you guys may have at the moment? So a poll has been launched. Please make sure that you complete the poll before you leave the session. Right. Are there any questions that you guys may have? Oh, there was no audio. Oh my word. I forgot I couldn't share sound. Oh, what a train smash. But I have attached the link. Don't worry. You guys will get the slides. I have attached the link to the YouTube video as well, just to help you guide through that. Then we probably share it here. Let me share it in the chat. Where were we? Let me exit that. Where can we? So let me copy that and share it in the chat, and then you guys can take a look at that because I forgot. I mean, like I stated in the beginning of the session, that we were having issues with the audio. So even with the closing, the audio won't be playing. So it's going to be a definite just goodbye. So next steps, I see there aren't any questions at the moment. No. And then you can't hear the video. Okay, so it was just not hearing the video. I have attached the link to the video in the chat. Hopefully that will help. Next steps, I just want to close off this guy here. Next steps, your assessment for K-means and hierarchical clustering MCQ is due on the 20th of July, 2026 at 11:59 GMT. So start learning now. The recordings to the session will be shared with you and you will find them in the ML-04-2026 Program Hub on eHub. And remember, you are not alone in the community. Let me keep that on a slideshow. You are not alone in the community. Make sure you engage with your squads, you ask for clarity, and you post your wins, challenges, and new insight on your squad spaces. Again, I have attached a link to a YouTube video as well as a project guide just to help you as you attempt that K-means clustering MCQ. There is a project guide that has been attached to help you through some of the questions. So I will close this off now, see that there aren't any questions. Thank you guys for coming. You almost at the end, and I'm happy to have walked through or been with you up until now. Wishing you all the best, and I will see you next week. Unfortunately, there won't be any music playing because I am unable to share sound on my side. But all the best for your MCQ, and I will see you next week. Cheers.